Okay, I want to welcome everyone to my lecture today. Today, I'm actually going to be walking you through another exciting topic in statistics. Give me 1 second. I'm actually going to project my screen. Okay, today we are starting a new topic called functions of random variables. And of course, this is actually going to be taken from chapter 6 of the textbook. Okay, then the outline today, I'm actually going to walk you through the function of random variables with some examples. Then from there, we're going to move to other statistics. Then we're going to have some examples as well. Okay, let me tell you this. If we have a random variable x, which can actually be a discrete or continuous type, okay? And if there exists another random variable y, where y is also a function of x, we can have a way to derive, knowing the probability function of a random variable x, we can actually derive the probability function for the random variable y. Because if x is a random variable, and a new variable can be expressed as a function of x. So that very new variable is also going to be a random variable. Okay. And of course, what we want to do is knowing the probability function of a random variable x. Okay, can we have a way to derive the probability function of a new variable that is also a function of random variable x? We have a lot of probability distributions that are derived, okay, from this kind of scenarios. And you know what? If we want to do that, we have approaches that we can use what we call the method of distribution functions. We can use method of transformation. We can use method of conditioning, and we can as well think about the method of moment generating function. But you know what? I four of us want to start today with the method of distribution function. Now take a look at what I have. I have x1 up to xn. That's original random variable. And this is the function. Okay. This is the probability functions of the random variable. But you know what? There exists a new variable u, and that very u is a function of what we have here. And what do we want to do? We are now seeking to obtain the probability function for the new variable u. And don't forget, the u that we talk about is a functions of the old variables. Okay. Now, how are we going to do that? Okay. So, what we're going to do using the method of distribution function is for us to find values in the x1 up to xn. Okay, and the space where an uppercase u equal to that, then we're going to find the region where the u is less or equal to, the an uppercase is less or equal to that, using the method of distribution function. You actually want to find the probability of a random variable, or taking less or equal to a realized value. Okay, so, and that's exactly why we are considering this, so that we'll be able to find the CDF. Okay, take a look at that. That's a CDF. Okay, and CDF is just the probability of an uppercase less or equal to u. And the moment we get the uppercase, the CDF, don't forget, what we're looking for is actually either the PDF or the PMF. That's what we're looking for, right? Depending on whether the new variable is going to be of discrete type or a continuous type. So before we can actually obtain a lowercase f, we need to first obtain an uppercase f. And you know what? After obtaining, if I want to obtain my uppercase f, what I'm going to do is to integrate that with the, with we need to integrate this by integrating this guy over the region. Okay, we are u less or equal to that, and at the end of the day, if I obtain my CDF, then I can obtain my PDF. That's finding the antiderivative, by finding the derivative rather, by differentiating this. Okay, when I have an uppercase F, which is a CDF, if I differentiate the CDF, I'm actually going to have a PDF. I'm going to say that again. Differentiating a CDF, which is an uppercase F, then it's going to take us to the destination. Okay, so this, what I'm describing right here, is what we call the method of distribution function. Okay, like I said, we have other method that we can use. Okay, but that is going to be the focus for now. Then I'm going to take you through an example now. Okay, now let's have an example right now. And the example is actually coming from a uniform distribution. The other time we did what I call a uniform distribution. Now take a look at that. Stores located on a linear city with density f of s equal to 0.05. The 0.05 here is more or less talking about is a uniform distribution taking the range from -10 to 10. Because when you integrate this guy now, okay, some of you may be wondering, how did they get this? And that is, you remember what we did the other time, that we said f of x equal 1 divided by b minus a. Okay, b in this case is 10. Okay, the maximum, so it's 1 over 10. Okay, minus, what is your a in this case is minus 10. So f of s would be equal to 1 over 10 plus 10, which is 1 over 20. Okay, so 0.005 is the same thing as 1 over 20. Okay, I wanted to take a look at that. Okay, so what I'm trying to talk about now, 0.05 is 1 over 20, and of course, you know how we derive that. It's using the uniform knowledge of 1 divided by b minus a. Okay, so, but you know what? This is f of s. Now we have a Korea in cos a cost of u equal to 16x squared. When you take a look at this, we got a new variable u, and it's a function of x. And don't forget, the original probability distribution for a random variable x is uniform. Okay, but you know what, the cost now is also a cost function. It's a random variable, but it's a functions of the conventional, the random variable x. Look at that, u equal to 16x squared. Now you know what we want to find right now. We are seeking now to obtain a probability function for the new variable u. Okay, guys, confirm again, if you guys are still hearing me clearly. Okay, thank you so much. Thank you for confirming that. Now we are seeking to obtain the probability function for u, okay, which is actually the cost, okay, the cost in Q, okay. And if you want to do that, we want to use the method of distribution function. And you know what? If you want to use the method of distribution function, what we're actually going to do, you need to first find the conventional variable, find x. Okay, solve for x. That's going to be the first thing you're going to do. Okay, software S is more or less like make the conventional variable, which is actually x, the function, make that express that in terms of the new variable. That's exactly what we're doing here. And at the end of the day, what is x? X is actually this guy. Okay, by solving that. Okay, now if x equal to this, okay, then it means I told you the other time, using the method of distribution function, we are actually going to be considering this, right? An uppercase u less or equal to a realized value. And of course, if I'm considering this, then what that means, my x is going to lie between the negative of this guy and the positive of this guy, which is exactly what I have here. Okay, can you see that now? Which is what I have here. Now, the moment I have the range now of x, then I'm set to obtain the probability associated with this. Okay, the probability associated with this guy here, okay, is this guy, which is the CDF that I talk about. So all what I'm going to do, I'm just going to come back here. Okay. Uh, I'm going to, you're going to see that there's no X here, right? If I have add X here, we would have plug in something. But for now, this is a constant, right? Okay. I'm just going to write that. Okay. When I write that, I'm going to integrate that using the range of X that we just find now. Look at the range of X. Okay. And when you do that, we have the square root of u divided by 40. If you take a look at what I have here, it's actually the CDF. Okay, and what is going to be the range? You got to define the new range. Okay, because the range we have initially was minus 10 to 10 for x, and don't forget that the new variable you are finding u equal to 16x squared, right? Now, what are you going to do to determine the range for you? You're going to plug in, what you have here. Okay. So, for the lower case of f of u is going to be 0, but the upper case, okay, you can use 10. So that would be 10 squared, right? 16 times 10 squared, 16 times 100. And that's why you have this. So this is a new range, okay, for what you have here. But you know what? This is not what we're looking for. Okay, because what we're looking for is an lowercase f. Now, what I'm going to do now is to differentiate this guy here. I told you the other time, differentiating an uppercase f, we actually give you a lowercase f, which is the probability distribution that we are actually seeking for. Okay, now, right now, this is the final answer now. This is the probability distribution of the random variable u. Now, some of you may be wondering, if I want to find anything that has to do with the cost, maybe I want to find an average cost, I want to find the variance of the cost of, then what I'm going to be using is going to be this probability. Is there anyone who want to ask question or who need clarification about this slide before I go to the next slide? Is there anyone? If you guys are good with my explanation right now on this slide, I need you to say yes or you comment yes if you're good with what I just explained right now. Okay, I think I'm only seeing one or two people. If there's anyone who doesn't really understand, please ask question. Okay, thank you so much.
I have
Okay,
a
it means you guys are
I have a
good.
question quick.
Okay, so that is how to use the method of distribution function. Okay, I want to walk you through another example right now. Okay, we are still on the method of distribution function. Okay, but you know what? The example that we use here, we are only talking about a random variable x. At time we could consider a situation. Oh, somebody says someone seems to have question. Okay, the person should go
Yeah.
ahead.
Okay, I'm
Did the
wondering how
person
you
send his chat?
derived
Let me
on.
see. Someone seems
Can
to
you hear
have
me?
a question. Yeah, go ahead. I saw his chat right now. Go ahead with your question.
I'm wondering how you'd find the mean with the probability function you
Can you
derived.
guys confirm again if you can if Oh, somebody said you cannot hear him. Oh, can you guys confirm if you're still hearing me? Okay, I saw a message in my chat right now, and somebody said, somebody seems to have a question. Who is the person? I think I'm listening now. Oh, somebody said, I'm wondering how to get the mean, how to get the mean with f of u. Oh, okay. If you want to get the mean with f of u, okay, of course, maybe you want to find the expected value of u, right? Of course, the expected value of u will be integral u f of u du. You're going to be making use of this. Have I answered the question now? Because if you want to get f of u, if you want to get anything that has to do with cost, you're actually going to be making use of the new distribution, the new probability function you just derived. Okay, okay. Somebody say this person say yes, thank you. Oh no, based on this, you can find the variance, you can find the whatever. We are no longer working with the this function, but we're working with a new one. Okay, so that is the essence. Now, this is going to confirm to you that some probability distributions they were derived from an existing probability distribution. Okay, thank you so much. Now, if you look at the example that we did here, we only considering one measurement of a variable. Okay, what if in a situation like the next example that we want to do right now, where we have joints. Okay, you could have a joint. Okay, we could have a joint like right now, x1, x2 are independent exponential with parameter theta. Okay, now we are the f of x are equal to this. Okay, and you know what? If x1 and x2 are independent, what happen? So what happened is that if the f of x1, according to what you're giving right now, it's actually 1 over theta exponential is power minus x1 over theta, and f of x2, okay, they have the same parameter. Okay, the two variables actually have the same parameter. Now take a look at this. We have f of x1 and we have f of x2. Okay, because because they say they are independent. Okay, what are you going to do? Because they say they are independent, you're going to multiply them to get the joint. Okay, so multiplying them now, you're gonna write f of x1 x2 equal, okay, f of x1, okay, multiply. Give me 1 second. Um, Give me 1 second. So f of x1 x2 will be equal to f of x1, okay, multiply by f of x2. So why am I using this? Because I've been told here that x1 x2 are independent. If x1 and x2 are independent, I can actually multiply, okay, they are marginals. Okay, and that was how I got this. That was how I got, give me 1 second. That was how I got this. Okay. Okay, so when you multiply the two exponential, that's what you're going to get. Take a look at that. Okay, but you know what? If you have that, you now want to find a new, we're seeking to determine a new probability for u, where u equal to the sum of the two variables that are distributed exponential. So which means what we want to find now, we are seeking to find f of u. Okay, we're seeking to find f of u, but this time around, u, a new variable, is a function of x1 and x2, which, and don't forget the x1 and x2, they are exponential distribution. And what are we going to do right now? The difference between the example that we're doing now and the first example that we did is that we actually want to go from two variables to one variable. We're going from variable x1, x2 to u. Okay, I'm going to say that again. We are going from variable x1 and x2 to u. But the other one, the last example that we did, we go from variable x to u. Okay, now we want to use the method of distribution function right now. So what we're going to do, um, an uppercase capital U equal to small u. Okay, implies, x1 plus x2 equal to that, then I need to find x1. Okay. If I want to find x1, one of the variable, then it's going to be this guy minus x2. Look at that. That's what I have here, right? And the moment I have this, the next thing I'm going to be doing is to be able to find this. Don't forget, I want to use the method of distribution function, which is actually the variable that I'm going to be considering. I need to consider the probability and of an uppercase u less or equal to the lowercase u. And you know what? This guy here is actually implies that x1 plus x2 is less or equal to u. Okay, if I'm considering this, then instead of having x1 plus x2 equal to u, I'm going to have x1 plus x2 less or equal to u, and that implies, okay, x2 less or equal to u, and x1 less or equal to u minus x2. Because what I'm trying to do, I'm actually going to have two range, because I'm going to have two integrals. You know why I'm going to have two integrals? I'm actually going to have two integrals because of the fact that, what I have is a function of x1 and x2. Okay, if I have x1, x2, x3, okay, I can also go from x1, x2, x3 to a new variable, which means I'm actually going to have triple integrals. But right now, because I want to go from x1, x2 to u, I'm actually going to have two integrals. Now, the probability of an uppercase u less or equal to small u now, then this is going to be, I'm going to have two integrals. And when I have two integrals, of course, I'm going to be 0 to u. Look at that. Then it's 0 to this guy here. Look at that. Okay. Then the next thing I'm actually going to write right now, I'm going to write the f of x1, x2. Okay. The joint. okay, this which is this one. Then I'm going to integrate with respect to the x1 and the x2. That's exactly what I'm doing here. Okay, if you want to start, you can start with a sequential integration. For of us integrate with respect to x1. When you integrate with respect to x1, you don't forget you're going to use this range from 0 to u minus x2. Then after that, then you're going to integrate with respect to s2. That is exactly what we're doing right here. And at the end of the day, you're going to see that what we got is actually initially we got the probability of u less or equal to small u. This is what we got. That is the CDF. Okay, this guy here is actually the CDF. Okay, and if I got the CDF, okay, this is the expression for CDF. Now if I got the CDF, how am I going to get the PDF? Or what I'm going to do to get a PDF, I'm going to differentiate this with respect to u. Differentiating, so which means what I'm doing now is going to be d du, okay, an uppercase of that will give me what I'm looking for, okay? So can you see that now? And that's exactly what we're doing here. So when you do that here, when you differentiate that, you're going to have this. And when you have this, this minus that plus, minus times minus, at the end of the day, you're going to have this. Look at that. You're going to have, so which means what we got now is actually this guy here. So this is my, f of u. And when you take a look at this, what we got, this is similar to gamma distribution that we've done before. Do you remember? I'm going to write a gamma distribution for you to be able to know if x follow gamma, okay, with parameter alpha beta, okay. You remember that we did is going to be f of x equal 1 over beta raised to power alpha gamma alpha, okay, x raised to power alpha minus 1 exponential raised to power minus x over beta, okay. Take a look at that. That's exactly what we're going to have. And you know what? If you take a look at this guy here, okay, when you plug in, it is looking as if our alpha equal to 2, okay, and our beta equal to theta. Okay, when you plug in alpha to be 2, okay, that is what you're going to have, and beta to be theta is going to give you this. And that is why I said, the conclusion here is that a gamma distribution is actually a generalization of the exponential. I'm going to say that again. What lead to gamma distribution now? Okay, because this is a gamma distribution with parameter alpha equal to 2 and beta equal to that. Okay, so which means what leads us to a new distribution called gamma distribution is the sum of the independent, is the sum of two variables that follow exponential. Okay, so which means a gamma distribution was actually derived from exponential distribution. Okay, but the way we did that is that the sum of the exponential distribution give rise to the gamma distribution. Okay, you guys confirm again if you guys are still hearing me clearly. Okay, thank you so much. If you really understand what I explained on this page, okay, if you understand what I explained on this page, I need you to comment yes or you say yes if you understand what I explained on this page. Okay, good job. Thank you so much. I'm so happy that you understand that. Now, we are done with the method of distribution function. Okay. Now, I want to walk you through another method that we can also use. Okay. The method is called the method of transformations. I want to tell you this. The method of transformation is very, very popular. Okay. Some people call it Jacobian transformation. Okay. Now you have f of x, okay, and you have a new variable u that is also a function of x. It could be decreasing or decreasing. And you know what this approach entails? If I want to go from f of x to f of u, okay, all what I need to do, okay, is to multiply the conventional f of s by the absolute value of Jacobian. Okay, this is an absolute value of Jacobian because my Jacobian that I'm actually gonna have and you know what here, the Jacobian here, My Jacobian for one variable is just going to be the s dy. Okay, it's going to be the s. Or for this one, I'm talking about u. Give me 1 second. Because I'm talking about u, the Jacobian here is going to be the s du. Okay, so that is the Jacobian. Okay, so then I'm going to find the absolute value of that. Then I'm going to multiply by f of x. But you know what? Before I multiply by f of x, I have to express my x as a function of u. Okay, so this approach that I'm explaining right here is for one variable. Okay, is for one variable. What of in a situation where I got two variables, like situation like this, where I got this one. Okay, we got two variables, x1 and x2. Okay, and what we're going to do using the method of transformation, if initially I have x1 and x2 and I'm seeking to get u, okay, I can't go from two variable to one. I have to go from two variable to two using the method of transformation. Then because of that, even if I'm giving u1, I'm going to create artificial one u2, because I can only go from x1 next to u1 and u2 to two variable. It should be 2 to 2 or 3 to 3. But at the end of the day, I'm going to integrate something out. Okay, I'm going to integrate the one I introduce out at the end of the day. And that's exactly, that is what we're trying to do right here. Okay, at the end of the day, since if what I'm looking for is u1, and I was the one that created u2. Why do I create u2? I created u2 maybe probably because method of transformation have to be either 2 by 2 or 3 by 3 or 4 by 4. And at the end of the day, the u2 that I created, I have to integrate the joints of u1 and u2 with respect to u2. Okay, so that I'll be able to get my f of u1. Okay, so that is it. Now that is the method of transformation. Now I'm going to walk you through an example right now. Okay, can you guys confirm again if you guys are still hear me clearly? Okay, thank you so much. Thank you for confirming that. Now take a look at that. We have a function given initially to be f of x equal to 2x. Okay, where x lie between 0 and 1, and we define a new variable u equal this. Now this is it. Let me tell you, I'm going to show you the question. That is the question. And what they want you to do is find f of u. That is the question. Okay. Now, um, I don't want to use method of distribution function. I want to use a method of transformation. But you know what? When you take a look at this, because I'm only considering x, okay, that would be one-to-one transformation. This is going to involve one-to-one transformation. I want to go from x to go to u. Now, if I want to go from x to, you know what I'm going to do? I will first find, I will solve for x. Okay, I will solve for x in terms of u. Okay, because let me tell you this. My own formula is this. My own formula is going to be, you know, I will need to fall first. My f of u is actually going to be f of x, okay, multiplied by the determinant of Jacobian. But you know what? This guy here, I need to have a situation where I express x in terms of u. Okay, I need to express x in terms of u before multiplying by determinant of Jacobian. Okay, and you know what? The Jacobian is actually going to be dx du. Okay, now I'm going to walk you through that now. Okay, I'm going to walk you through that now. If you take a look at this, I said the very first step is, okay, solve for x in terms of u, which is this guy, right? Okay, and after that, go back to f of x. Okay, the f of x, is equal to 2x, right? If the f of x equal to 2x, what is your x now? What is your x? Your x now is this, right? Then plug it in. Then you've already plugged it in. This is what you have now. Okay. And after getting this, you know what you're going to do next? Then you need to come back here. What is dx du? Okay. What is dx du? Dx du, okay, is going to give you 1 over 500, right? Okay. Take a look at that. Then you're now going to use 1 over 500, which is this is the Jacobian here. Okay, the S, the U is the Jacobian. But don't forget, in case you get a negative, you have to do absolute value of that. Then you're going to use 1 over 500 to multiply this guy here. When you are using 1 over 500, which is a Jacobian, to multiply this guy here, then you are no longer in f of x, but you are in f of u. Okay, so this guy now multiplied by this, we know that is what you have here. Now, what do you have now? You have f of u. Take a look at that. You have f of u now. Some of you maybe then we need to determine what is the range. What's going to be the range for you? Okay. Now, the range for you, you're going to come back here. U equal to this, right? Plug in the lower case of x. We plug in 0. What is 10 plus 500 times 0? That is going to be 10, right? That's why you have 10 here. Then plug in 1 to x. That will be 500 times 1. That's going to be 500, right? 500 plus 10, 510. So therefore, I have a new distribution now. My f of u now is u minus 10 divided by 125,000. And you know what? My u now lies between 10 and 510. Okay? Lies between 10 and 510. Take a look at that. Is there anyone who doesn't really understand this page? Is there anyone who doesn't understand that page? Is there anyone? If you really understand what I've done here, I need you to say yes, or you comment yes. If you really understand. Oh, good job. Thank you. Now, the what we've done here is just method of transformation, but this is for 1 to 1. Okay. Here we move from x to u. Okay. That was what we did right now. Okay. But what if in a situation, can we have a situation where we got to move from two variables to two variables using the method of transformation? Okay. I'm actually going to walk you through that as well. Okay. Now, uh, I'm still going to revisit that as time goes on. If I want to go from two variables to two variables using the method of transformation, but before I do that, I want to walk you through another method of the method which is called the method of conditioning. You've done conditional probability, right? Okay, now you have u is if u is a function of x1 and x2, right? Now the conventional variable that we have is x1 and x2, but you are defining a new variable u, and we're seeking to obtain the probability density function of a new variable u by using the method of conditioning. Look at conditioning. Now, for method of conditioning, we need to first find what is the PDF of u, okay, given one of the variable, given s2, okay? And of course, we can do that by transformations, okay? And by transformation, we got to say, okay, let's an uppercase s2 be equal to a lowercase s2. Then what we're going to do, we need to first obtain the uh, the joint density of u and s2. Now, if I want to obtain the joint density of U and S2, of course, I'm gonna use this. Don't forget what we've done before. The probability of A given B is probability of A intersection B divided by probability of V. And in that case, if I want to find this guy, it's gonna be this multiplied by that. Okay, that's exactly what we're trying to do right here. This is a joint. Okay, the PDF of the joint of U and X2 is going to be the product of the conditioning, okay, which is trying to tell you X and X2, U and X2 are not independent, okay? U and X2 are not independent, okay? Now, the next thing that we're actually going to do is after getting the F of U, X2, the joint, of course, after getting the joint, the whole thing is going to be so easy because what I'm looking for is f of u, or what I'm going to do is to integrate out this with respect to s2. Look at that. So if I want to get my f of u, you know that the moment I have this guy here, okay, my f of u would be integral f of u x2, of course, the s2. I think you know that. That's what we're going to do. That's what we did before. Okay, we're going to integrate out x2. And don't forget the f of u x2 is the product of that. Okay, that is the product of that. I think you know that. Okay, so this is what we call the method of conditioning. Okay, that's what we call the method of conditioning. Okay, now let us now have an example on the method of conditioning. I walk you through the method of distribution function, the method of Jacobian transformation, but right now we want to have an example on the method of conditioning. Okay, now you are given that x1 follow beta distribution. We've done beta distribution, right? Okay, I think you still remember the beta distribution. Uh, you know, uh, Let me tell you this: x follows beta. Okay, distribution with parameter uh, alpha, beta. Okay, the f of x is actually x raised to power alpha minus 1, 1 minus x raised to power beta minus 1, then divided by um, gamma alpha, gamma beta. I think I have gamma alpha plus beta. You remember what we did before, right? So that is actually, uh, you know, the f of x. If x follow a beta distribution, okay, I think you know that. Now, it said x1 follow a beta with alpha equal to 2 and beta equal to 2. Okay, so when you plug in that here, when you plug in, so which means for f of x1, okay, if you want to find, if you plug in that, so it means x1, 2, that would be 2 minus 1, right? Okay, and 1 minus x1, that would be 2 minus 1, then gamma, okay, into 2 plus 2, okay, divided by gamma 2, okay, give me 1 second, um, give me 1 second, actually, okay, I'm actually gonna clean that now. The one I wrote. Okay, now gamma two, gamma two. Now, when you take a look at this one here, okay, what is 2 plus 2? Gamma 4, right? And gamma 4 is actually going to be um 3 factorial, right? Which is going to be 6, right? This guy here is going to be 6, right? Gamma 2 is 1, gamma 2 is 1 factorial, another gamma 2 is 1 factorial. Now, if I want to rewrite the whole thing, I'm actually going to write f of x1, okay, equals 6, okay? This is going to be x1 into 1 minus x1. And that was how we got, that was how they derived this. Can you see that now? That was how this is derived. Okay, they are actually using a beta distribution, okay, defined as this, and the parameter alpha equal to 2, beta equal to 2 has already been given. No, that's how we derive this. Okay, and we have another variable s2 that follow beta distribution with alpha equal to 3 and beta equal to 1. If you plug in alpha to be alpha equal to 3 and beta equal to 1, here you're going to have you're going to have this guy here. Okay, you're going to have that guy here. Okay, and you know what is the range of x when you're talking about beta distribution? Is from 0 to 1, because I told you the other time we use beta distribution to measure proportion, right? Okay, when the proportion is a random variable. Now we have our x1. Well, now we have our f of x1 to be this, and we have our f of x2 to be this. But you know what? We are seeking to get u. And what is u? A new variable u. And the new variable u is a product of x1 and x2. And don't forget, the x1 follow beta distribution and the x2 follow beta distribution. They have different parameter. Take a look at that. Okay, now we want to use a method of conditioning. Do you know that this same question, we can use a method of transformation, we can use a method of distribution function. Okay, but right now I want us to use, you can try that. Right now I'm using the method of conditioning. Okay, I want to tell you, if you use a method of transformation or you use a method of distribution function, you're still going to get the same results. Okay, you guys confirm again if you guys are still hearing me clearly? Okay, thank you so much. Now, you know what you're going to do now? You have your f of x1 to be this, and you have f of x2 to be this, and you are seeking to get u, a new variable, which is a function of x, is a function of x1 and x2, but is a product. Okay? Now what are you going to do? You need to find x1. Okay, you need to find x1, and x1 is going to be u divided by x2. I think you know that. Okay, if x1 equal to this, then you need to get, what are we getting here? We're getting the Jacobian, right? Okay, which is going to be the x1, uh the x1 du. And what is the x1 du? It's going to be 1 over x2. Okay, after that, what are you going to do? You need to find f of u given x2. You remember the other time, if you want to, we, before we can get f of u x2, before we can get this joint, we need to first obtain this guy here, right? Okay, we need to first obtain this guy here. Don't forget, we already know f of x2, right? The f of x2 is beta, right? It's a beta distribution, right? We need to get f of u given x2, and that's exactly what we're trying to do. The f of u given x2. Okay, now what you're gonna do? You're actually gonna come back here. Okay, when you come back here, you're gonna plug in what is x1. Okay, we just find x1 to be u over x2. You're gonna plug in u over x2 in place of x1. That's what we've done. Look at that. And after doing that, then you multiply by the Jacobian, but not just Jacobian, the absolute value. Don't forget, it has to be the absolute value of Jacobian, because we don't want a negative value. Okay, we don't want a negative value. Take note of that. Okay, and that's exactly what we're doing here. Okay, now that is how we're going to get, with this we're getting the conditional now. Okay, we got f of u given x2, and the moment you get f of u given x2, okay, then you are set to get the joint. What is the joint? The joint is going to be the product of this guy and the marginal distribution for x2. Okay, now f of u given x2 is the whole of this. Okay, that's what I'm putting right here. Can you see that now? That's what I'm putting right here. Okay, then multiply by f of x2. The f of x2 is this guy. Look at that. Oh my god. Okay, oh my god. Okay, that's what I'm putting here. Do you know I can twist this question? You know how I can twist it? I can twist it. I can say find f of u given x1. Okay, find f of u given x1. What if I ask you to find f of u given x1? Okay, you have to start from here. Okay, you have to start from here. You have to do all this using this. And at the end of the day, you're going to multiply by this. But right now, what we're doing is f of u given x2. I can twist the question. Okay. If I were you, okay, why can't you also try? You can also try f of u given x1. Try that. If you have tried that, you can send that to me. Maybe I can give you an extra credit. Okay. Now, this is where we are now. Okay. The f of u comma x2 is going to be the conditional that we got right here, multiplied by f of x2, which is this guy. Okay. Now, at the end of the day, you simplify, you do some algebra, you're going to have this. Now, the moment you have this is a joint, right? For u and x2, right? What are you looking for? You're looking for u. You're looking for f of u. Now, if you're looking for f of u, then you're going to integrate out x2. That's what we're doing now. Take a look at that. Okay, you want to integrate this guy with respect to x2. That's what we're doing. And if you want to integrate with respect to x2, okay, you're actually going to use the range from u to 1. Okay, you know why you're using the range from u to 1? Because u lie between, uh, somebody said, I thought we are looking for f of u given s2. This is what you are looking for. Okay, you are not looking for f of u given s2. This is, you are looking for f of u. Okay, this is what you want to find. Okay, but before you can find that, we need to first obtain f of u given s2, because we're using the method of conditioning. The method of conditioning entails using for first finding f of u given s2, which is what we find right here. Okay, what we find right here is not the result. Okay, although in a question I can ask you to find this, after asking you to find this. Okay, now take a look at this. Give me 1 second. I'm actually going to show you something now. What if in a question, okay, maybe I give you this, okay, and I said, 1, find, okay, f of u given x2. 2, find, okay, f of u, the joint. Then 3, find f of u. Did the person understand now? I can ask you to do all of that. Okay? Before you can actually find this, you need to first find this. And before you can finally find f of u, you must have find the first two. Did the person get the question now? The person that asked the question in the chat, did you get it now? Okay. I'm super excited that you get it now. Okay, so what we're looking for is f of u. Okay, and at the end of the day, since now that I have my joint, then I'm going to integrate with respect to x2 using the range. And finally, this is my f of u. Don't forget, what is my u? U is the product of x1 and x2. Because another question can be asked, what is the expected value of u? Okay, what is the variance of u? Then you're going to be using this function here to be able to do that. The resulting expression to be able to do that, that is what you're going to be doing. Okay, so this is how to do that. Is there anyone want to ask question before I move on? Is there anyone want to ask question? Okay, now uh we have what we call the method of generating function. Okay, in the method of generating function, this is what we want to do. um if you have x and y that are random variable, and the two of them have CDF, okay, and the two of them also have moment generating function. You've been taught how to derive a moment generating function. The ms of t is a moment generating function of a random variable x, and my of t is a moment generating function of a random variable y. Okay, then uh if the moment generating functions, if two variables have the same moment generating function, automatically they're going to have the same CDF. Okay, so this actually implies this. The moment they have the same moment generating function, they're going to have the same CDF. I think what I'm going to do, I'm going to stop here today, and I'm going to start from here tomorrow, because I don't want to rush you. We're in the last chapter in the semester. I don't want to rush you. Okay, so I'm going to start from the method of moment generating function today. I mean tomorrow. Now, what we've done today, I just walk you through how giving a function of a random variable, and if you're giving a new random variable which is a function of the original one, we can actually derive the probability function for the new one using the method of distribution function, or the method of transformation, or the method of conditioning. Okay, we can actually use all this one, and we're going to get the probability distribution of a new random variable. That is just the essence. Some probability distributions were derived, okay, from scenario like this, and I walk you through how um, a gamma distribution, uh, which is a valid probability distribution, can be derived from from the sum of the exponential distribution, from the sum of the exponential distribution. Okay, is there anyone want to ask question before I go away today? Is there anyone want to ask question? Is there anyone that need clarification? Is there anyone? Okay, if you really understand what I taught today, if you really understand